So let's get into it. Today, we are growing a little bit more on some of the stuff that we have seen last time. We are talking a little bit more about this two-dimensional motion, and we are going to try a very rough dive into a topic that I still wonder about whether or not we should even include it in these slides. So let's get into that disaster as we see it. From last time, as we were talking about these things, we said, okay, two-dimensional motion, right? Now there's two of them. It's not that much different from one-dimensional motion, though. Really, what we see here is two sets of equations, and we can split it right down the middle, and they're all the same kinematic equations that we have been working with so far. Now, the only difference is that we have one set for x, we have one set for y, but you'll notice that these equations are not anything new. They're actually just using our old one-dimensional equations, but now two sets, two columns. And you'll notice as well that they're kind of independent from each other, right? The only thing that actually ties these two together is this delta t. The time where these things are happening is shared between the two sets of equations, but other than that, nothing else, right? If I throw a ball, when it hits the ground, where it's at in x and y, that happens at the same time, when it hits the ground. When something reaches the top of its arch, that happens at the same time, when it's at the top of its arch. So we can use that delta t to kind of tie these two sets of equations together, but for the most part, that's the only thing that actually ties them together. And that is handy and not at the same time. I would probably argue it's more useful than not, because that way we can kind of treat it like one-dimensional motion while we're overworking in that column, and we don't have to worry about what's going on over there. We just have to focus on the stuff that we've got in front of us. But most of the time, as we're seeing these things in two-dimensional motion, we have a very common problem, specifically describing what we call projectile motion. So, say you're tossing a ball to a friend, or say you're tossing a ball at the ground, or say you're throwing something at somebody, whether or not you like them, I don't know. In any of those scenarios, what we typically imagine here is that if we are going with our standard drawings of x and y is going up, x is going, I don't know, to the right or something, then our acceleration in the x direction is 0. There are no anti-gravity guns that we know of or have access to that are pushing it or pulling it in air. But there is an acceleration in the y direction because of gravity, and that is going negative g. So downwards by 9.8 meters per second squared. With all of that information, then we could split up some of these things. We could say, well, okay, well, if it's going at some angle, then some of that velocity is starting in x, some of that velocity is starting in y. Not always the case, but perhaps it is in this scenario. And with all of this information, we've actually got pretty much everything that we could possibly need to describe any number of scenarios. There's a lot of different things that we could do with these. So, in exploring this, there is a lab associated with today. I bring this up right now. It is all about this projectile motion. You get access to a cannon that you can fire and watch what happens to the range and all sorts of stuff like that. It is not a very intensive lab, and I'm not going to recommend starting it right now, because right now we're in the middle of a lecture. But after the lecture, taking some of these concepts, thinking about some of these problems that we've been working on, maybe try to recreate them in that simulation and see if you get similar results. See if it spits out the same things as what we've been expecting. So, it is in mastering, yes. So, I have a problem for us, and if you have done the reading, you'll actually already know the final answer to this thing. But why would you look it up right now? Get the practice in, right? That's the whole point. What we have is something being launched from level ground. Let's say we have a cannon of some sort or something else like that, and we are trying to launch this thing. We're interested in knowing a few different details. First, and most, let's start on this for now. I want to find what is the maximum height. If we launch this thing off, what is the maximum height h that it could possibly reach? That height should only depend on our initial velocity, the initial angle that we launch it off, and other constants like g. Furthermore from that, we can find something what's called the range, which is essentially how far did it move in x. Range means delta x. What I'm thinking here is that I want to spend the first 5 or 6 minutes on this one. And we're going to talk about part A. And then I'm going to go through part A, what I think for part A. And then we can spend another few minutes working on B and C if you were still on part A or something else like that. But what I'm going to recommend here, my strategy from last time, is I'm going to recommend draw this picture out for yourself. Get a given box, all the variables you know. Find the one thing that you're interested in. From there, start writing out these kinematic equations in the 2 columns. Cross out the things that are 0, underline the things that you don't know. That is my general strategy. If you're not sure how to approach the problem in the first place, doing these steps will essentially guide you to the equations that are currently solvable and what equations you need some more information to find first. So, first 5 or so minutes, try to get through at least part A. If you get through part A, start jumping on to the next things. But let's at least focus on drawing out part A and figuring out what's going on there. Okay, now, I would argue, y velocity to 0? Perhaps. It depends on which part of the problem you're talking about, but let's focus on part A for now, and let's see what we get for this thing, and I'm going to make some suggestions based on what we see in this part. And then going from there, we can kind of maybe see what similar steps we would take for part B. So, the first thing that I want to do is I would like to draw this thing out. Right, drawing this thing out is always a fantastic step. Having a working drawing pad is also always a fantastic step. Things used to be so easy. Over time, everything seems to just break on me. We've got that. We've got that. We've got whatever our object is being launched at some angle. Call this vector v0. And then what I can also imagine here is that we're going to have some sort of trajectory that looks maybe something like, I'm not good at drawing parabolas, something like that. That seems reasonable. Maybe a little bit too wide on top, but that's all right. We are talking about a maximum height h right in the middle of this thing. Right? Can we all agree it's probably right in the middle? That's where the highest spot is going to be. So I'll label h right there. And then I'm going to say that is theta. Okay. So, part A of this problem. As we're going to have this, what I'm going to do is I'm going to label these things, and I'm going to say up here, call this state 1. I have already used a not symbol, so I'm going to call down here at the very beginning state 0, where we start, our initial, state 0, state 1, state 2. For the purposes of finding maximum height, what is the height that we are going to reach when we launch this thing off? I really don't care what happens after we've reached that maximum height, right? I'm going to kind of draw the divide there. I am only interested in state 0 to state 1. So let me do this all in kind of like a red color, and we'll say, so part A, state 0 to 1. Now what I'm going to do is I have my picture, I have a rough idea of what's going to happen here. I need to start drawing out what all of my variables are, and I'm going to try and organize these things in terms of things that I know, things that I don't know. So what I am given, let's start with that. And what I'm going to do here is I'm going to split up my colors depending on things that are true of the problem as a whole, and then things that I can kind of extrapolate from those. So the things that I've got in black here are going to be the things that we actually know. What variables are we given in this problem? What do we think? The initial, I would agree with that. We are given v0. We also do have acceleration. V final, let me come back to that one in just a second. You are correct. I agree with that. But I have v0. I have theta. I could also make an argument here that acceleration being negative g in the y direction, acceleration in x being 0, and now I agree with everyone's points here. Think about what happens at the very top of the arch here. At the very top of the arch, even if we just toss the thing right up in the air, right? Not even launching it off at some angle or anything else like that, just toss it up in the air. At the very top, we stop, then we fall back down. That stop that is where our y velocity is 0, but not our entire velocity, because we can kind of see from our picture here, at this top spot right here, our velocity would look something like this. Let me just call this v1. v1 at this point is purely horizontal. Then it starts falling back down. Then it picks up a y velocity again, but in the negative direction on the second half of this picture. So I will agree with that. What I will say is that vy1 is going to be equal to 0. The last thing that I can do here is I can also say that x0, y0, can we all agree that those are 0? We've got everything that we need. The last thing that I will do, and here's kind of like a circumstantial thing, what I will say is that for our initial launch here, these are things that we know, but not necessarily things that are given variables. I could also argue that my initial velocity in x and my initial velocity in y are equal to v0 cosine of theta and v0 sine of theta. Both of those things are things that I technically know, but I'm writing them out like this because these are not variables that I am given, in a sense, but they are variables that if I see them in my equations, I know exactly what to do with them. Vy1 is my velocity up here at the very top. So, let's start with this then. We have our list of variables that we are given. We are tasked with finding h, also known as y1. So, I'm just going to take this thing from my straight off approach here, right? I'm going to start with x, then I'm going to do y. I'm going to keep them in two separate columns. We're going to work with them as we see them. Starting with x, I could say that delta x is equal, or even better yet, let me just do this thing as x final. So x1 is equal to x naught plus vx naught times t plus 1/2 a of x t squared. Wonderful. Now I'm going to go through and I'm going to cross out the things that are 0. X naught is 0. Acceleration in the x direction is 0. I'm going to highlight the things that I don't know. I don't know x1. I don't know t. Cool. This is useless. Right? This doesn't give me anything. Maybe it could, but certainly not right now. What about the other two equations in x? Are those actually useful for me? I know I'm talking about writing these things down, but I want to talk about, like, do we need to? Why not, though? That's the real thing I'm after. Why are the other two kinematic equations in x really not going to give me anything? What's the big sticking condition for both of those? Can even kind of write it out and see. They depend on an acceleration. Both of them do. If the acceleration is 0, then what we have effectively done is say, hey, look at that. The final velocity is same as the initial velocity. And all right, you know, that's cool, but it doesn't help us. It doesn't get us any farther in the problem. It states a fact that we could probably already look at the picture and say. We knew there was no acceleration of the x. We didn't expect it to change velocity. So writing this down really isn't going to give us anything new. I can kind of ignore those two equations. If you're still a little bit shaky on some of these projectile problems, go ahead and write them down anyways. But when you look at these things, you'll start to realize, hey, this just doesn't give me anything new. Right? This just repeats information or solidifies information that I already did know. They're not actually going to help me progress through the problem anymore. Okay, so we've kind of exhausted everything that we could have in x. Let's go over to y and see if there's anything different that we could pull from over there. I'm going to do the exact same thing for y. I'm going to say y1 is equal to y naught plus vy naught times t minus 1/2 gt squared. And I'm just going to go ahead and plug in g while we've got it. Cross out the things that I know. And that's it. As we've got this thing right here, I don't know y1. That is the thing that we're after. I don't know t. Okay, well, maybe we can keep moving forward. That's not solvable right now either. And even if I wanted to combine it with my other x equation, I still have 3 unknowns, but only 2 equations. So even if I wanted to use these equations, I'm not ready yet. Let me keep going down the list. The next thing we could do is Vy1 is equal to Vy0 minus gt. So I know Vy1. I know that's 0. I can cross that out. I know Vy0. I don't know t. Here is my first instance. I see a path to the end of my problem. If I solve out my equation right here for t, I move up to the next step, I plug in t, I find y1. That would work. But I'm lazy. And if I'm trying to be as lazy as possible, let me just see what else we can come up with here. Let me try one more equation. Vy1 squared is equal to Vy0 squared minus 2g delta y. This one right here is of particular interest to me. Vy1 is 0. I've already got my acceleration plugged in. Delta y is y final minus y initial. So that's just y of f, right? Our initial y was already 0. So I could say 0 is equal to Vy0 squared minus 2g y of f. Right here, y of f is the only thing we don't know, and it's exactly what we're looking for. Right? Or I shouldn't say y of f, I should say y1. This is exactly what we're looking for, though. And the reason I like this one so much is because I have to do less calculations to get to my final answer. Right now, I realize we had to write a lot of things down for this. But what we're building to is the intuition to be able to look at the variables that we have and to figure out, before we write these things down, which equations would best serve the scenario that I'm in. Which equations have all of these variables already included in some way or another that I can relate together to find the thing that I'm after. Nothing in either my given or my find box mentions t, right? So if I were to go with my first 2 equations, I would have to find an extra variable. I would have to write down extra equations and solve them out properly before I could get to my final answer. If I instead go with my 3rd equation in y, I skip that unnecessary variable. I can jump immediately to finding y1. So let's try it. Now that we're here, let's rearrange this thing. Let's say y1 would be equal to Vy0 squared divided by 2g. I'm going to replace Vy0 because that's not technically one of my given variables. It is derived from my given variables, but I want to get a complete picture here. So what this would actually be is V0 squared sine squared of theta divided by 2g. And that is my final expression for the height. Sine was our y component of that initial velocity. So if we zoom in on this thing, if I'm drawing out the triangle for this thing, I have that side, I have that side. I'm not doing a very good job of drawing the triangle, but this would be the y component, this would be the x component. Following my SOHCAHTOA, sine would be the opposite side length, Vy. Cosine would be the adjacent side length, V of x. So, what I want us to try now. Here was my methodology for finding the height, for finding things going on in the y direction. The solving process is not exactly the same for finding the range, but it's not super different. It's the same set of equations, I just need to change them around a little bit. Now keep in mind, I keep talking about what's going on in state 1, but if we're talking about the range, then we're very interested in what actually goes on in state 2. Now, one thing that is different, if you have been working with me in any sense or anything else recently, then I've been labeling states in a very similar way. But things like the flea problem or the elevator problem or some of these different problems where we have a change of acceleration, that is not the same thing as what's going on here. I have labeled those things in a similar way, but it's not the same because in a case like this, there is no discontinuity in the motion of whatever we're launching, of our projectile. right? Because this entire time we had gravity pulling down the exact same way. Nothing changed with our x velocity. Nobody suddenly smacked it midair or anything else like that. Unlike what happens in the elevator when you have a change of acceleration. So here, what we've got is a continuous 0 to 1 to 2. We can directly relate 0 and 2. That is what I would recommend. Go through part B and C. Take another 4 or 5 minutes here. Go through part B and C. Directly relate 0 and 2 in a similar manner that we just did here with our given variables. Now we're solving out for delta x instead of finding what goes on in y. But we still need both columns to make this thing work all the way. Think about the information that you know. Highlight the information that you don't know. See if you can piece together which equations are going to be useful from those. And we'll come back in just a little bit and talk about it again. All right, so let's close out this problem. So this time around, we're no longer interested in what's going up here. We're much more interested in where we end up, right? Our range value, but it's really just delta x. So I'm going to take my same picture as before. I'm not going to change anything, but now let's do all these parts in blue, right? To say, hey, we're working on part B. State 0 to state 2. So a lot of the things that I have will carry over. There's no problem with that. Let me start with the things that I'm given. If we think about all those, well, I am given v naught. I'm given theta. I know that my acceleration in the y direction is still negative g. I know that my acceleration in the x direction is still 0. I know that x naught and y naught are still 0. Those were true for the last part. They're still true for now because all of these are still describing state 0. What about state 2, though? What other variables do we know about state 2? What do we think? I know that my final y position is 0. I would agree with that. Y final, or I would call that y2, would be 0. I agree with that. Anything else? Vx is still a constant. I would agree with that. I would agree with that. I think I would call it there, though. Right as I've got these things, that's kind of all the variables that I've got, right? And we look at our last list, that was kind of a similar scenario, right? We had all of these other things, and then Vy1 was our extra little bit here. And here, instead of that, we have that y2 is 0. That's our extra little bit on the rest of this information. That is our thing specific to our state 2, but really nothing else. We don't have a lot more information about what's going on there. We could relate time, but I don't necessarily want to do that. And let me talk about that in just a little while here. The other things that I've got, just in the same way as last time, I could say Vx0 is equal to V naught cosine of theta. And I'm just doing this to make sure that we know when we see these variables, they're not quite given variables, but we can easily transform them back into the things that we do have. I'm asked to find delta x. So let's start there. Let me take my kinematic equations in x and let me highlight what I've got, what I don't. I could say delta x is equal to Vx naught times t plus, and I'm just being explicit here, 1/2 ax t squared, but again, we have no acceleration in the x direction in this problem. So that's out, but I don't know delta x and I don't know t. Same argument as last time. There's no x acceleration. The next two equations that I could write in x are useless to me. They will not provide any new information. They will confirm my belief that the final x velocity is the same as the initial x velocity, but it won't give me any useful information for solving the rest of this problem. Instead, let's save all of our time. Let's jump to the y equations. I'm going to do the same thing here. Delta y is equal to Vy naught times t minus 1/2 gt squared. Delta y, I start at 0, I end at 0. Delta y is 0. I don't know t, and that's it. Unfortunately, in this one, there is not one clean equation that will just give me my answer right from the beginning, right? Nothing we can do on the right column is going to give us anything better than finding t, because if we wanted to just solve this thing out automatically, it would have to be on the x side of this. We have to find t as an intermediate step between these two. And since I've already got an equation right here that's going to solve out for t, I'm going to call it right here. Let's use this one. Let's solve out for t. Let's take it back to x, plug it in, get our answer. Solving this thing out, what I have is 0 is equal to v naught t minus 1/2 gt squared. What is 0 divided by t? Any guesses? Still 0. Yeah. Right? Why would I solve a quadratic equation when I could solve not a quadratic equation? Right? I'm not a huge fan of quadratic equations. I've got a personal bias against them. Not a big fan at all. So what I'm going to do is I'm going to divide both sides of this equation by t. This 0 really doesn't care. The rest of this is suddenly a lot more simple. Got all this information. That looks all fine to me. Whoops, t. Should not forget that, the most important part of this. So I'm going to solve this out for t now. When I solve this out for t, we should get something that looks kind of like this. 2 times vy naught divided by g. Perfect. That's exactly what I'm looking for. Because now, if I notice, vy naught, that's something that I have in my given bank. G, that's a constant. This has everything we need in a nice little package of variables that we already have. Let's move this over to delta x. So what I'm going to do here is I'm going to draw, let's see how well I can do this. Let's draw this arrow down like this, and let's try and get this one to go like, that could have looked worse, I guess. But now what I'm going to do is I'm going to plug in that t exactly as I have it. So delta x is equal to vx x naught, plug in t. That thing right there. Now, as a quick little reminder here, we do want to put this thing into only variables that we actually know. So I can't leave this as vx naught and vy naught. I have to plug in for my given variables. V naught, theta, g, things like that. So I'm going to take this another step down. I'm going to say, okay, delta x should then be 2 times v naught squared cosine of theta sine of theta. Oh no. Oh no, we made an ugly equation. Oh no. Technically, this works. This is fine. This is fulfilling all the conditions. It is a final expression dependent on only the variables that were given, and it tells us the range. Can we just look at that though, or can we solve out for the maximized range angle? Yeah, I would argue we could simplify this a little bit more. Yeah, I would agree with that. One thing yeah, I would think the only other way to do this, if you are familiar with your trig identities, maybe you look at this and you say, I know what this is. If you're not as familiar with your trig identities, and I can tell you, when I was taking the final exam for this class, when I was taking this class years ago, and I got a problem just like this one, and I did not remember my trig identities, what I did is I threw it into a calculator, and I found what the maximum range would be, just graphing it out and then manually finding the maximum from that. That will technically work. I don't know if I recommend it, but it technically works. What's a little bit better to do, a little bit more rigorous, a little bit less depending on your calculator doing this, is there is a particular trig identity that will help us very much here, and I do see it in chat already. The trig identity is that if I have 2 times cosine of theta times sine of theta, that is equal to sine of 2 theta. Combines those two together, and that is wonderful, because now we can take that expression, delta x is equal to now V naught squared sine of 2 theta divided by g. It's a little bit simpler, it's a little bit nicer, more pleasing to look at, but more importantly, we can conceptualize what goes on with that sine a lot easier. What is the maximum value that sine of anything could possibly be? 1, right? The most it could ever be is 1. The least it could ever be is -1, and in between that, maybe 0. Sine is limited to the values of that unit circle. So, if we wanted to maximize our range for a given angle, we know right off the bat, sine is only at most going to contribute 1. What angle do I have to plug into sine to make it equal 1? Technically, if I'm plugging in an angle into sine, it's 90 degrees that makes it 1, but in this case, since I have 2 times theta, 90 divided by 2 would give me 45 degrees, gives maximum range. I would agree with all that. We just want to be rigorous with that. There will be problems in the future where we have to talk about what we do with sine and the angles that we can plug in and everything else. So remember that. Sine is maximized when it is 90 degrees, so if we see 2 theta, to make it 90, we need to plug in 45 for theta. Whenever we know that sine, let me draw out the unit circle for this one. What we've got is if we had our big unit circle, we know that sine is technically limited to being equal between, that is almost centered. We know that at most, sine might give us 1, sine is equal to 1, or sine is equal to -1. Those are essentially the bounds of what we might be able to find from this thing. If we plug in some angle, right? The question was, what angle would that be? It has to be 90 degrees to be 1, 270 to be, I didn't leave myself enough space here, 270 to be -1. We're interested in this one because we want to maximize our range, right? Any angle other than that would give us something less than 1, would be taking away from our maximum distance. So if I know that I need 90 degrees to be inside, and I see 2 times theta, theta being 45 gives me my magic 90 degrees to make sine the most it could possibly be, getting the most out of our firing at this point. Okay, so one of the things I am going to say on this one, we're going to do a little bit of jumping around because I have to talk about a topic that I'm not happy about talking about, but if you are among the students that this feels very uncomfortable right now, that is okay, right? We're going through this stuff. We are suddenly seeing a lot of equations moving around, a lot of algebra moving around. There's a lot of descriptions, and you can kind of tell these problems are taking more and more time as we go on. What I'm going to ask, if you have not already, if you really don't know how to approach these problems, if you're a little bit sketchy on it, but you're mostly getting through, a little bit of practice is probably all you need. If you don't feel like you're getting these on your own, send me an email, chat with me, let's set up something so that we can actually talk back and forth a little bit about these things, and we can get everything ironed out. But send me an email, let me know, and we can work on something from that. For now, what I'm going to say is let's skip this one. I'm going to come back to it. But I want to talk about something that I'm not super happy about talking about, and let me kind of describe why. Relativity, perspective, Galilean transformations. The whole point of this is basically this idea that I am sitting right here, maybe somebody else is walking, maybe somebody else is driving in a car, maybe we all see the same thing happening. Regardless of who sees it and how they might be moving, we should all be able to agree what happened and why at the end of the day. If we can't do that, something's wrong, right? Physics should not matter who you are, where you are, how you're moving, what you're doing. When you observe something, we should all be able to agree that that thing just happened just like this. And if we don't agree on that, then we should at the very least be able to talk about some way that we could agree if only we could describe what perspective we saw that thing happening. My problem with this, I think this is a very useful thing. I love this, but you might notice that when reading about this, this gets 2 pages. And from then on, we're really not going to talk about this again until the very end of 192. I've got some problems with that. I'm not very happy about how that's done. I don't think it's very useful to spend a lot of time talking about it right now when we're not going to come back to it again anytime soon. I do still want to discuss it, and I am going to talk about the mathematics behind it, but I'm going to focus a little bit more on making sure you guys understand conceptually what's going on. And if we don't completely understand the math that goes behind this, I'm honestly not super worried about it, right? I think it's not worth the amount of time to put into it because we're not going to get a lot of use out of it. We will see some things about it. We will have some conceptual things about it. But beyond that, solving these things out properly, I'm not super worried about it because it's just not going to be useful for us right now. So, with that being said, let's talk about these concepts. Let's imagine you've got some crazy cool blue car with flames on it, so you know it drives fast. If you are sitting in this car, driving along the highway going at 70 miles per hour, and you are passing a semi-truck, on your right side, when you turn your head, you don't see them moving at 60 miles per hour. You see them stationary. If they match your speed, if you are riding side by side with this semi and you're at exactly the same speed, you don't see them moving, you see them stationary right next to you. When you're sitting in the car, you don't see the road staying still, you see the road coming at you. Right? From my perspective right now, I think I am stationary, if I'm being honest. I'm sitting right here. Maybe I'm bouncing around a little bit, but for the most part, I would argue that I'm pretty stationary. I'm not moving in a vehicle. I'm not running. I'm not doing anything else like that. But at the same time, I also have to kind of rectify that with the fact that I am currently on the surface of a giant spinning ball that is spinning around another even larger ball that is spinning around an even larger ball in the galaxy that is hurtling through the vastness of empty space. I am not actually at rest. I am constantly moving. But from my own perspective, I don't think I am. I see myself as being stationary, and that's something that we have to contend with. That from our own perspective, when we look down at our hands, look down at our legs, we think we are stationary. Everything else that we observe is moving relative to us. And that's the entire thing about this joke right here. Each of these people see themselves moving relative to the other person moving relative to them. And that joke in this context is hilarious, and nobody can convince me otherwise. But part of this, when we're talking about relative speed or relative velocity, we have to kind of contend with these ideas that other people might be seeing different things, but at the end of the day, the physics still works. We just have to have some sort of transformation that goes between our two perspectives to make sure that we agree. So, if I see the car moving at 70, or if I'm in the car moving at 70 miles per hour, and the truck is moving at 60 miles per hour, speed relative to the truck would be 10 miles per hour forward. If you're in the car, you see the truck moving 10 miles per hour backwards. If you're coming head on towards each other, you each see each other moving at 130 miles per hour, assuming, of course, that you're not like doing this or something else because you're going head on with the semi. But assuming you're not, you would see each other moving at 130 miles per hour because, again, your perspective is that you're stationary. The truck moving towards you looks like it's moving even faster. So, talking about all these things, oftentimes when we're discussing these, we talk about events. Events are things that happen at a place and a time. You probably already knew that, but that's our definition that we're going to be using here. A reference frame is an observer, or how we measure that position and time. That is to say, if two different observers, two different reference frames, see something happen at the same time, then the relative motion between the two is the transformations that we do to make sure that we agree that what we just saw happen was the same. Everything was all right. So, how we're going to describe these. Let's call our home frame, our rest frame, S. And I know these pictures are impossible to decipher, but but let's just go focus on the conceptual parts here. That's what we're trying to grab. If frame S, the observer in S, sees an event happen right here, Y prime, S prime, I shouldn't say Y prime, the S prime frame sees it happening maybe somewhere slightly differently. Relative to them, they might see it somewhere different. Let's go with something that we could all possibly see. If the sun were to explode right now, I might see it happening wherever the sun is, somewhere over there. I don't know where it is right now. Wherever the sun is, I would see it happening over there. From where you're standing, maybe you see it happening over there. From where everyone is standing, we would each have our own perspective of where the sun exploded. But we could all agree that the sun exploded, and using these equations, using these transformations, we could all agree that it happened at the same place, even if from our perspective, it happened in different places. Instead of being forward, maybe it's behind you or something else like that. So these also take into account that one of these observers might be moving. So in this case, what we've got right here is that S prime is not actually just a stationary frame, it is a moving frame. S prime is moving at a velocity capital V. They see the event happen at a different place depending on how long they've been moving before the event happens. So from S's perspective, we see R. From S primes, we see R prime. Everything to do with the prime frame, S prime, all has a prime attached to it. So R prime, as we will see later, there's other things that go with that as well. But this equation down here tells us how to relate those two together. I didn't do a very good job of boxing that in, but that's the transformation to go back and forth between the two. We can do the exact same thing with velocity. We'll get to that in a second, but the fact that these are vectors means that we can split these up into individual x and y transformations. So we can split these up as we need to and work with it just like we have been with vectors this entire time. The vector math is easy. Conceptualizing it is perhaps a little bit more difficult. We could also reverse this in just the exact same way to say, okay, well, if r is equal to r prime plus v of t, v times t, then r prime is equal to r minus vt, the other way around. But in this way, if we both see the event happen and we both measure what our respective r's are, then we can use this transformation and we should agree on where it happened. So for some of these transformations, as we might draw these things out, we can also agree that a velocity might be different from different perspectives. If we take a derivative on each piece of these, then we end up with two equations right here, a regular and an inverse, you might say. The t goes away, but that is to say, kind of going back to what we saw with the truck, right? If we are side by side, matching the speed of the truck, then we don't see the truck moving. It is stationary relative to us, right? It's not going anywhere. But somebody standing on the side of the road would see both of us moving at whatever speed we were. So, between all of these things, and especially the second set, I want to try a problem. Let's just do this instead. Let me walk through how I would solve this thing. And let me do one more thing. Let me show this little video demonstration. Hopefully the frame rate is not so terrible that you can't see this at all. But this is what it would look like. So imagine, and this is a good time to imagine it, you're driving during some sort of snowstorm. You see snow falling down. When we're stationary, it looks like it's coming directly down, right? We agree on that? As we start moving, it stops looking like it's falling down. It starts looking a lot more like it's coming towards us, right? Now, we shift our perspective. We turn our head. Now it doesn't look like it's coming towards us. It looks like it's moving past us. If we turn backwards, it looks like it's moving behind us. If we turn our perspective again, it looks like it's... But arguably, nothing has changed. The snow is still falling down. Our perspective of it might have changed, but at the end of the day, we know that it doesn't really matter what our perspective is. The snow's falling down. If we're moving towards it, then it looks like it's coming this way for us, but somebody standing on the side, we know how to get back and forth between our descriptions of what we just saw. So let me try and demonstrate this one in a problem. I don't want to try and go through this right now because, again, it's just a little bit rough. But let's imagine the scenario here. Steve practicing throwing up into the air for some reason. I don't know, baseball things, I guess. But what he's doing right here is he throws the ball upwards and east, so 63 degrees above the ground, at a speed from his perspective of 22 meters per second. Nancy drives past Steve at 30 meters per second and drives right past him as he releases the ball. According to Nancy, first, what is the speed of the ball, and then what direction is the ball traveling? So here's what we're going to do. I'm going to try and draw this out, and I'm going to try and describe this thing as we go through it, and hopefully we don't make a huge mess of this thing. Let's just see what happens. The speed of the car was 30 meters per second east. Okay, so as I've got this thing, I'm going to try and draw out these reference frames, and let's see what we can do with those. So here is... Steve throwing a ball. Right, look at that. What perfect form. Here's the ball. Here it is moving at some velocity according to Steve. I'm even going to draw this out, and I'm going to say Steve standing still will be our S frame. Regular S. At an angle, call it theta. We know that initial speed, the magnitude of it at least, is 22 meters per second. We know the angle is 63 degrees. Now, at the same time, Nancy is passing by. And I'm not going to draw these exactly overlaying, but they should be. I'm just trying to give myself space. Look at that car. I don't know. It looks more like a really poorly drawn truck. There's our car. There's Nancy inside of the car. From a different perspective, you know what? I'm even going to go so far. Let's do this in a slightly different color. Let's do this in blue to just really establish, hey, these are two different scenarios. Here is our... That looks a little bit more like a car than last time. I don't know. Whatever cars look like. S prime. So Nancy, the second observer, the S prime frame is moving forward at a speed capital V. Capital V is 30 meters per second. How do we go back and forth between these two perspectives and agree on something at the end of the day? So what we're going to need to do is we're going to need to take these velocity transformations. So what I'm trying to look for here, I'm looking for the speed of the ball from Nancy's perspective, V prime, and then I'm going to be looking for the angle of the ball from Nancy's perspective, theta prime. So let's go back to our transformations. We say, okay, we are looking for V prime stuff, right? So that's the equation that we want to use. That is, V prime is equal to V minus capital V. And that's exactly what we've got right here. Vectors are wonderful tools because, again, we can split them up. I don't want to deal with this as V. I want to deal with this as X and Y. Because I know that V is moving in, from my perspective here, the X direction, right? So let's split this up. Let's say V prime of X would be equal to the X velocity of the ball when it starts minus capital V is only in the X direction. So that'll be minus V. Vy prime is equal to Vy minus, there's no capital V velocity in the Y direction, so that'll be a minus 0. So as I've got these two things, what I'm going to need to do here is I need to actually find values for Vx and Vy. I could do a transformation to say V of X should be equal to V cosine of theta. V of Y should be V sine of theta. These two things should be 10 meters per second, or right around there. I know there are some decimal points here. And the other is 19.8. No, that's not the thing I want. What did I have for this? 19.6. meters per second in the x, 19.6 in the y, from Steve's perspective. So, when we plug these things in now, when we go through these transformations, Nancy sees an x velocity of, instead of positive 10, of negative 20 meters per second. And the y velocity unchanged. So then, now that we have the two components, we could say that the v prime vector is negative 20 I hat plus 19.6 j hat meters per second. Now we take our common definition of direction and of magnitude. So the magnitude of this would be using Pythagorean's theorem. So 20 squared plus 19.6 squared to get 28.01 meters per second. That is the speed of the ball from Nancy's perspective. The direction, theta prime, is going to be just taking each of these values, Vy prime over Vx prime, for an angle of 44.4 above negative x. That is to say, if we were to actually graph this out, what does the ball look like it's doing? The ball looks like it's going this way. If we were going to be using these concepts more often, I would love to hit this harder. The reality is, sometimes this is going to be a useful thing. Like, eventually you're going to be in a position where you do need to talk about these things, but I think by the time we talk about it in 192, you have mastered motion. You have more than mastered motion. You are completely comfortable with all these equations by then. It is so much easier to talk about different perspectives and transformations between those perspectives once you have that experience. I'm not overly worried about hitting these things right now. I want to mention them because I know some people will not take 192, and getting a sense of relativity and everything else is a good thing to have. But ultimately, now is not the time to hit it very hard. So conceptually, if we understand it, I am happy with that. So, let's go back to something that is going to be a little bit more common for us. So we're skipping 4-6. It's in there if you would like. I will have a solution posted up for it later. But 4-4 is, I think, the one that's a little bit more interesting for us right now. So this is very similar to our range problem. The big difference is that if you have ever seen anybody do shot put or anything else like that, they're not like scooping it from the ground and launching it that way, right? You're throwing it from this angle right here. That is, the starting Y position is above ground. Y initial is no longer 0. Y final is. It hits the ground, and that's where we call it. But what we have in this problem here, what I'm looking for, is we're going for a very similar scenario. We're trying to find the range based on all of this stuff. But now, with an extra variable that is not 0. Let me play that again. As soon as I pick up the pen, it freaks out. But what I'm going to ask you to do, drawing the problem, is a very big portion of this thing. What I'm going to try and recommend you to do is go through the exact same scenario that we did with our range problem. Draw this thing out. Label some different parts. Think about where you want to start and where you want to end this problem. Write out all of the variables that you know. Write out everything that you're looking for. Then start drawing our kinematic equations out and figuring out which of these are going to be effective in solving this, which of them are not going to be so useful. I'm going to say let's take the next 7 or so minutes and work on that, and then we'll come back together and see what we've got. Okay, I think it's a good time to start taking a look at this one. So, step one, not just because it's part A of the problem, but because you should be doing this for all of these problems. Step one is going to be to draw a pretty picture, right? Pictures like this that look beautiful, like fridge-worthy stuff, right? So here's what we've got. What I'm going to draw here is, I'm going to imagine, I'm going to imagine that we are going to start at some height. We are going to go some distance in x. So I'm drawing that nice and long, so we've got plenty of space to draw this stuff out. Call it y, call it x. We are starting, the shot put starts from like right here, right at our initial y. It goes up at an angle. Call this angle, or call this vector, v naught. Call this angle, theta. Then this thing is going to fly kind of like this. I imagine it will, at least. Right? And we said a pretty picture that is fridge-worthy, and this is it, I think. This is my peak. I'm going to label a couple other things on here while we're here. What I'm going to draw is delta y, and I'm going to call this delta x, and I just want to label these in my picture so I have a complete picture. Now, my given variables. If I say we start at 1.8, we end at 0, then I know that my delta y ought to be negative 1.8 meters. We go down at final minus initial, 0 minus 1.8. Delta x, that's the mystery to be found. My magnitude of v naught, if we go back to this thing, we say, hey, that was 12 meters per second at 40 degrees. Okay, I know that my acceleration in the y is negative g. I know that my acceleration in the x is 0. And is there anything else we have? I think that's about it. One other thing that I will draw on here is that we know that Vx naught is V naught cosine of theta. Vy naught is V naught sine of theta. And the only reason I bring up both of these again is because if we see those variables, then we know that they are numbers we technically have, right? So we don't need to label those as unknown variables. We do have those. They're just not necessarily numbers that we were given in the problem. They're one step away from that. We need to find this delta x. So, okay. Let me dive into it. Let's see what we've got. I'm going to start by drawing out my x column, right? Say delta x is equal to Vx naught times t plus 1/2 axt squared, 0. I don't need to draw anything else. There's nothing else over here. I'm just going to skip straight to 0. Cool, we've seen this one before. No acceleration in the x direction means that equations 2 and 3 just aren't going to give us anything new. Our x velocity is constant the entire time, which is nice to know. It makes the problem simpler, but it doesn't contribute any new information that could help us solve this thing as we have it right now. I don't know delta x. I don't know t. I've got nothing else that I can really do on this side. I've got to immediately move to the y side, which you'll find is often the scenario. If there's no acceleration in the x direction, you're probably not going to get a whole lot out of x. You probably need to look at what's going on with y. So let me go to there. Let me say delta y is equal to Vy naught times t minus 1/2 gt squared. If I look at this thing, I can say, okay, well, I know delta y, I know Vy naught, I don't know t, but that's the only unknown variable in this problem right here. Now, realistically, do we know anything about the final y velocity? Yes or no? No, we do not. We don't know anything about the final y velocity. We cannot call it 0. I will harp on that one again. We cannot call it 0. As soon as that shot put collides, let's go back to that video, actually. Let's watch what happens. Let me try and skip ahead to where this thing actually collides. Somewhere in here, somewhere in here, somewhere in here. Let's pause when we hit bam. That's a little bit after, but look at what happened there. We left a hole in the dirt. There was turf that flew up. The ball bounced. There was a thud. All of those things are part of what happens during a collision. Do any of our equations talk about any of those parts? Do they talk about the turf flying up? Do they talk about the sound, the vibration from the thud, or the dirt beneath getting compressed? I don't think so. That's a complicated problem. That's a lot more complicated than what we're doing right now. So when we're talking about final velocities and final positions, really what we're doing here is we are imagining what happens, and I'm going to draw a copy of this thing, and I'm going to take this thing and I'm going to try and move it. Let's get in super close. We are trying to talk about what happens right, get even closer, zoom way in, right here. Whoop, there. That's as close as we get. That is what we call final position, final velocity, all that jazz. Not here. Now we have collided. Now things have changed. There's a new acceleration. The ground is pushing back up against it. We have to focus on right here, right before we actually collide. And that means that we don't know anything about what happens there. We have no information about what's going... Oh, I didn't mean to delete all of that. We have no information about what's going on at that final velocity. So we don't need that around. We just need this other stuff. And I want to bring that up because I know a lot of people always want to say that a final velocity is 0, and that is very rarely the case. But anyways, because we don't know anything about the final velocity, similarly, equations 2 and 3 of our kinematic equations don't give us a lot. I could write them out real quick just to be sure, but Vy final is equal to Vy initial minus gt. Well, we still don't know t, not yet at least, and we don't know that final velocity. I could find the final velocity by using my last equation, but it's kind of like the same argument when we were doing with range, right? I could find final velocity from this, and then I could find t from that, but why would I take 2 equations to do what I could do in one? So either of these equations, I'm not focused on these things. I don't want to use these things. I could, but I don't want to. I don't think it's the easiest way to go about this. So let's focus on the thing that we can work with. This right here. We have to use a quadratic formula for this thing. And realistically, what I would probably recommend, at least for these things with numbers, is that you use some sort of calculator for these things. There are online calculators. There are online quadratic calculators. I imagine many of your handheld calculators will have programs already on them to solve these things out for you. Use them, right? They're tools. Why wouldn't you use them? But to do that, I'm going to rearrange this thing into our common form that we see for these. So this would be minus 1/2 gt squared plus Vy naught t minus delta y. From our good old classic, this is A term, this is B term, this is C term. That final equation, if you haven't seen it in some time, would be t is equal to negative b plus or minus square root. Video is frozen. Oh no. I think I'm still active on my end. Is that true for anyone else currently? Okay. Okay. I think you are unfortunately in a bad spot of internet. But this is the quadratic equation that solves out for such things like this. Quadratic formulas, right? There was a pop song about it at some point. This right here has a plus and minus in it, right? That means there are 2 possible solutions. Let's talk about those. When we go through and we plug this thing in, ideally in a calculator, because that's the easiest way to do this, we would find 2 different times. Those times are either 1.78 seconds or negative 0.21. Which of these makes sense? It's certainly not the negative time. Negative time, what does that mean? I don't have anything from that, right? What this is is that the algebra is giving us a solution. This negative time, the algebra doesn't care what's physical, what's not physical. The algebra is going to give us a solution that it thinks seems reasonable, and that negative time algebraically represents essentially what would happen if the ball had fallen backwards instead, backwards in time. That's why this works out so nicely when we're dealing with quadratic formulas, because technically speaking, for our range, when we were doing this thing over here, when we were looking at this, our initial state, when we got to divide by t, and we could get rid of that answer completely, that was a solution that t is equal to 0. That is to say, we're asking, when is y 0? Y was 0 when we started. Y is also 0 way out here on the right side. In this case, y is 0 behind us and in front of us. The behind us answer doesn't make any sense. We are going to disregard it. T is equal to 1.78. That fits with what we're describing. So that's the time that we're actually going to use. We take that answer. We go back to our initial equation using delta x, now with our new good friend t. Plug that in. Plug this in. Delta x being v naught cosine of theta times t. We should find that our delta x at the end of the day should be something like, where did I put that number? 16, I have 16.37 meters. Again, if you have something slightly different, it's probably just a difference in how we rounded things. I would be happy with anything nearby this. Okay. So for right now, and I think some people have already realized this, that's what I've got for today. Thank you very much for being here.